you haven't already watched the first rational graphing video, you might want to go back and do so then, because I'm going to be talking about things in this video that you will have no idea what they are unless you watch that one. So I'm just going to jump straight into it. Remember, what we're going to be doing for all of these rational graphs is we're going to be looking for the vertical asymptote, the end behavior asymptote, the x-intercepts, the y-intercepts, the holes, if there are any, and the domain and range. So let's start out with a function. Let's graph the function y equals x minus 3 over x plus 6. This is a good way to get us started to remember how to find all of these things. Now, this does not need to be factored any further, so I can go ahead and start finding all my things. Vertical asymptote is where the denominator equals 0. So in this case, it's when x is negative 6. So I'm going to go ahead and graph that. The end behavior asymptote, if the degrees are the same, is going to be the ratio of the numerator over the denominator, or 1 over 1 in this case, which means our end behavior asymptote is y equals 1. X-intercepts are the things that make the numerator equal to 0. So if I have x minus 3 in the numerator, my x-intercept is going to be 3, 0. Y-intercepts are where the x is 0. So we can plug that in. We'd have 0 minus 3 over 0 plus 6. So we end up with negative 3 over 6, which is negative 1/2. So our y-intercept is 0, negative 1/2. Now we didn't cancel anything out, so we don't have any holes in this case, and I can go ahead and graph one of my branches. However, I don't know what the other branch is or where it's at, so then we're going to use a test point. So let's choose a test point on the other side of the vertical asymptote. I'm going to choose negative 7. You just evaluate the function at negative 7. So I get negative 7 minus 3 over negative 7 plus 6, which is negative 10 over negative 1, which is 10. So I know that 7, 10 is a point, or negative 7, 10, excuse me, is a point on the graph. And now I can see where my second branch is. Once you have your function graphed, you can do your domain and range. And since we don't have a hole, these are relatively easy. The domain goes everywhere except for the vertical asymptote. The range is going to be everywhere except for the end behavior asymptote. And we're done. That was just sort of a simple example to get us back in the swing of things. We'll look at a few trickier types of rationals in the next few examples. So thinking about those things that we did in the first example and what you remember from the rational graphing number 1 video, let's go ahead and let's graph this thing. I don't actually have to factor anything, so I can go ahead and get started. The vertical asymptote is the number that makes the denominator equal 0. So in this case, it's going to be x equals 7. The end behavior asymptote, if the degrees are the same, is the ratio of the leading coefficient over the leading coefficient. So in this case, it's 1 over 1, so my end behavior asymptote is at y equals 1. Now, the reason I included this in the hard version is that the factor on the top, the numerator, is just x. Remember, we're looking for what makes that factor equal to 0. So in this case, it's just x equals 0. So the x-intercept is 0, 0. It's at the origin. The y-intercept, we'll plug in a 0 for all your x's, although if you're pretty savvy, you already know what it is. 0 over 0 minus 7 is 0 over negative 7, which is 0. Well, that makes sense. We had 0, 0 as the x-intercept. 0, 0 is also the y-intercept. It's where it touches the y-axis. And we didn't have any holes in this case, so that's not applicable here. And we know enough to sketch one branch. We need to find our other branch, though, so pick a number on the other side of the vertical asymptote. I'm going to choose 8. I would end up with 8 over 8 minus 7, which is 8 over 1. So the point 8 is also on my graph. That helps me see where the second branch is, and I can sketch that in. Now I can do my domain and range. And in this case, with no holes, the domain and range are relatively easy. The domain is going to go all the way over to that vertical asymptote. And the range is going to include everything but that end behavior asymptote. From here on out, I'm probably not going to look at the range because our graphs are going to get a little sticky and the range is going to be hard to determine from what we can see. So we're going to focus on domain. Domain is kind of what really the most important part about our rational graphs anyways. You'll see where that comes into play when we look at inequalities too. So this one is similar to the other one. It looks a little bit flip-flop though. Again, we do not have to factor anything, so we can go ahead and start finding our stop. Vertical asymptote. What's going to make that denominator equal to 0? The denominator just has a factor of x. We're looking at x equals 0. So our vertical asymptote is the line where x equals 0. Right along the y-axis here. Our end behavior asymptote is the ratio of the leading coefficients if the degree is the same. Since the degree is the same, I have a linear over a linear. I have 2 over 1. So my end behavior asymptote is just y equals 1. The x-intercept is going to be what makes the numerator equal to 0. So what's going to make 2x minus 3 equal to 0? It's not just going to be 3. We have to actually solve this. So our x-intercept is going to be at 3 halves. That's about 1.5. I'm going to go ahead and graph that. The y-intercept. Well, now again, you're going to plug in a 0 for all your x's. So you're going to get 2 times 0 minus 3 over 0, which is negative 3 over 0. We can't divide by 0, so there actually isn't an x-intercept in this case. Or, a y-intercept in this case. Which makes sense, because that's where our vertical asymptote is. So we do not have one here. There is none. We didn't cancel any factors, so there's not any holes either. Now this just gives me enough information to do one of my branches. I need to find the second branch. So I'm going to choose something. I'm going to choose negative 1. That means I have 2 times negative 1 minus 3 over negative 1. Which is negative 5 over negative 1, which is 5. So the point, negative 1, 5, is on my graph, which means I know where the second branch is. It's up in that top quadrant there. Domain and range, again, we're going to go everything but those asymptotes. Same for the range. And we're done. We found all of the critical information about our rational, and we graphed it. Even though this one doesn't look like it has to factor, we actually can simplify it a little bit. So, if we look at the numerator, it has a GCF of 10. So we could factor out the 10, and we would be left with x plus 2. You want to do this, it's going to make finding your attributes easier. When we factor the denominator, we're going to factor out a 4. So then we have x minus 4. We can simplify this a little bit. 10 over 4 we can simplify to just say, 5 over 2. So we're going to have 5 times x plus 2 over 2 times x minus 4. I wanted to do this because, again, it makes my graphing easier. Vertical asymptote, what's going to make the bottom equal 0? It's just going to be 4. End behavior asymptote is the ratio of the leading coefficients, and in this case, it's going to be 5 over 2. I could do this with 10 over 4, but you'd have to simplify it anyways. So my end behavior asymptote is going to be 5 halves, which is about 2.5. X-intercept, number that makes the numerator equal to 0. Good thing we factored it, because that makes it easy to see that our x-intercept is going to be negative 2. Our y-intercept is going to be just plugging in a 0 for all of those x's. So when we do that, we end up with 5 times 0 plus 2 over 2 times 0 minus 4, which is going to be 5 times 2 over 2 times negative 4, which is going to be 10 over negative 8, which is negative 5/4. So our y-intercept is going to be 0, negative 5/4, which is about negative 1.25, so we can see that on our graph there. That means we can go ahead and graph that branch. Good deal, we know where that's at. There weren't any holes because we didn't cancel anything out, so now we need to choose a test point for our second branch. I'm going to choose 5. And again, I'm going to go with the simplest version of my function. So I'm going to do 5 times 5 plus 2 over 2 times 5 minus 4, which gets me 5 times 7 over 2 times 1, which is 35 over 2. So that's going to work out to be a big number, bigger than my graph. However, that at least lets me see that my branch is going to be up here in that first quadrant area. Now we can do our domain and range, and again, with no holes, this is relatively simple. Look at me using my fractions. Yeah. And we're done. So there's all of our attributes, and there's our graph. All right, we have another one we have to factor. I know we have to factor that because I can factor that denominator. X plus 3, that's as factors as it gets. But x squared minus 9 is the difference of squares. So this is going to be x plus 3 times x minus 3. So I can see I have a common factor. I'm going to have a hole in this case. When we write our simplified answer, I can clearly see what the denominator is going to be. It's going to be x minus 3. I have nothing left on the numerator. Remember, this is the same as saying 1 times x plus 3. So it's really 1 over x minus 3. That's my final simplified answer. So now that we have that, we can go ahead and find our information. We know our vertical asymptote is going to be what makes the denominator equal to 0. So our vertical asymptote is going to be at 3. And behavior asymptote. Usually when the degrees are the same, we can just find the ratio of the leading coefficients. In this case, the degrees are not the same. I have a higher degree on the bottom. Well, think about this. If you were to look at your simplified fraction, I would have no x's. So that would be like saying 0x. So that means that I would have a 0 over a 1 if I were going to use the trick from before. So my end behavior asymptote is going to be y equals 0. 0 over 1 is 0. So let's go ahead and graph those two things. Now our x-intercept is what would make the numerator equal to 0. What would make 1 equal to 0? Nothing. So there isn't an x-intercept, which again makes sense. Look at where your end behavior asymptote is. You can't have any points on that. For y-intercept, we plug in a 0 for all of those x's. So I end up with 1 over 0 minus 3, which is 1 over negative 3, or negative 1/3. So my y-intercept is at the point 0, negative 1/3. I do have a hole in this case. I did cancel something out. I canceled out the factor x plus 3. So my hole is going to be at negative 3. Now I need to plug that in order to figure out what the y part of the hole is. So I have 1 over negative 3 minus 3, which is 1 over negative 6. So negative 3, negative 1/6 is where the hole is at. I'm just going to have to do my darndest. My stylus doesn't let me be too exact. Alright, so we can graph one of our branches. Now I need to find the second branch, so I'm going to choose a point on the other side of the vertical asymptote. I'm going to choose 4. So So I have 1 over 4 minus 3, which is 1 over 1. That lets me see that I have the point 4, 1 on my graph. I can go ahead and sketch that in. This sort of makes sense if you think back to transformation form. We actually have transformation form right there. We know that it hasn't been shifted up or down, but it has been shifted 3 to the right. This was important for us to start with the original function, though, because we needed to worry about that hole. We're going to have to think about that when we do our domain and range as well. Our domain is going to start at negative infinity, but it's going to stop at the hole before it hits the asymptote. Then it's going to start up again on the other side of the hole until the vertical asymptote. Start up again on that and go to infinity. Our range also needs to consider the hole. So I go from negative infinity up to the hole, which is negative 1/6. Start up again after that. Go to 0, because that's my end behavior asymptote. And start up again after that. So there we found all of those attributes and graphed that kind of tricky function. Hooray for more factoring. Alright, this one's a little bit sticky. The numerator, we have x squared plus x. So I can factor it. It has a GCF of x. Factor out the x, and we're going to be left with x plus 1. The denominator, well, that's also got a GCF of x. So I'm going to factor that out before I try to factor it any further. I have x squared plus 2x minus 8, which actually could be factored further. So I know my numerator already. That part's done. My denominator, I know that I'm going to have what multiplies to be negative 8 adds to be 2. It's going to be x plus 4, and it's going to be x minus 2. So now I can see that I have a hole with the factor of x. That lets me know that the x value is going to be 0 at my hole, because what makes x equal 0? 0. Now let's go ahead and write the simplified version so we can use that to help us make our graph. I have x plus 1 over x plus 4 times x minus 2. That's what I'm going to use to find all of my stuff. So it looks like my vertical asymptotes, well, I have 2 of them in this case. I can't have x equal negative 4, so one of them is at x equals negative 4. Nor can I have x equals 2, so I also have a vertical asymptote at x equals 2. It's going to change the shape of your graph. You're going to actually have 3 branches instead of 2. Our end behavior asymptote. Remember, that tells you what happens at the ends of the graph. Again, the degree is higher in the numerator than the denominator. So I have 1 in the numerator, and I have an x squared in the denominator. So I have 1x over 1x squared. Well, again, think about x squared. How many x squareds do you have in the top? None. So it would be 0x squared. So I'm going to have 0 over 1, and my end behavior asymptote is going to be 0. Now I know you're going, but wait a minute. X-intercept. That comes next. What would make the numerator equal to 0? It would be negative 1. So we have negative 1, 0 as an x-intercept. Here's what this tells me. Remember, that's an end behavior asymptote. It doesn't tell you what happens in the middle of the graph. So it is okay to cross it when we have graphs that have branches more than 2. So in this case, it will cross it. In fact, it touches it right there at negative 1, 0. That's okay. We're going to see what this graph looks like in just a second. Now, let's think about our y-intercept. Normally, the y-intercept is the point when x is 0. But remember, our hole was in x is 0. So we actually don't have a y-intercept in this case. The y-intercept and the hole are going to be one and the same. So let's go ahead and let's find the other part of the hole so we can see that point. We're going to plug in a 0 for all of our x's. So I have 0 plus 1 over 0 plus 4, that's plus sign, times 0 minus 2, which is going to be 1 over negative 8. So negative 1/8. That's where the hole is going to exist. Now, this is a little bit tricky because I do not know hardly anything except the middle part of my graph. And even then, I only know part of the middle part. So we're going to need to do a lot of test points. We're going to need to choose a test point over on both other opposite sides of both of the vertical asymptotes. So I'm going to choose the test point 3, and I'm going to evaluate the function at 3. When I do that, I end up with 4 over 7 times 1. So that leaves me with 4 over 7, 4/7, which is a little bit over a half. So that lets us see where one branch is going to be. Now I'm going to choose something on the other side, -5. That's going to leave me with -4 over, let's see, -1 times -7. So that's going to leave me with 4 over 7 again. So I have that point up there. That lets you see two of your branches. Your branches are actually up here. That's okay. Now we need to figure out what's going to happen in the middle. I already kind of know what's going to happen on one side. I know that it goes down like that, following those vertical asymptotes. I need to know what happens on the other side too, so you need another test point. You can choose -2, -3, either one works. I'm going to choose -3. When I plug in -3, I get -2 over 1 times -5, which is -2 over -5, which is positive 2/5. So what's going to happen in the middle is it's sort of going to do a little snaky thing and follow those vertical asymptotes. This is kind of a crazy graph, which is why it's in the harder. Graphing rationals number 2. But it didn't involve anything different that we had to do. We just had to choose a lot more test points. Now, I'm just going to look at the domain in this case. Our range is a little bit tricky. Well, really, it's everything but the whole. If we're just focusing on domain, we can see that we start at -infinity. We stop at the first vertical asymptote. We start up again after that. We stop at the whole. We start up again after that. We stop at the second vertical asymptote. We start up again after that, and we go to infinity. Really, any rational graph could have many vertical asymptotes. We probably will look at most 2, and more often than not, you're going to have one of the standard graphs that we've been doing prior to this. That last graph was a doozy, so let's see what this one works out to be. We're going to start out with factoring. What multiplies to be -6 and adds to be +1? X plus 3 and x minus 2. What multiplies to be -8 and adds to be +2? That would be x plus 4 and x minus 2. So we can see that we do have a hole here. We're going to have a hole when x is 2. I'm going to write that down already to help me remember. And our simplified fraction that we're going to be looking at is x plus 3 over x plus 4. Hooray! This one's not going to be as gross as the last one. Vertical asymptote. What makes the bottom equal 0? It's going to be x equals -4. I'm going to go ahead and graph that. And behavior asymptote, well, that's going to be the leading coefficient over the leading coefficient because the degrees are the same. So that's going to be 1. X-intercept. What's going to make the numerator equal to 0? In that case, it's going to be -3. Y-intercept. Plug in a 0 for all of those x's. So you get 0 plus 3 over 0 plus 4, which is 3/4. So our y-intercept is going to be at 0, 3/4. Now our whole. Again, you're going to plug that x value in. So you're going to have 2 plus 3 over 2 plus 4, which is 5 over 6. So the whole is at 2 and 5/6. So we can clearly see where one of our branches are, and thank goodness we only have 2 branches for this case because we only have one vertical asymptote. we need to choose a test point to find the second one. So I'm going to choose negative 5. So we have negative 5 plus 3 over negative 5 plus 4, which is negative 2 over negative 1, which is 2. So that tells me that the point negative 5, 2 is also on my graph. And we can go ahead and sketch our second branch. It is so not a right angle that is curved, I swear. Now we can find our domain. Like I said, we're really going to be worried about domain in this case, so we're going to forego the range. I know you guys can do that if needed. So negative infinity to the vertical asymptote. From the vertical asymptote to the whole. And then from the whole all the way to infinity. Things are so much easier when you only have 2 branches. Alright, this is going to be our last example. So in this case, I do need to do a little bit of factoring. And with what multiplies to be 4 and adds to be negative 12. Sorry, what multiplies to be negative 12 and adds to be 4. It's going to be x plus 6 and x minus 2. So I wanted to do something where we had another couple vertical asymptotes. So in this case, we can see that we're going to have 2 of them, both of our vertical asymptotes. We're going to have negative 6, and we're going to have 2. So I'm going to go ahead and graph those. Next comes the end behavior asymptote. Well, we have no x squareds on top and 1x squared on the bottom, so we're going to have an end behavior asymptote of y equals 1. X-intercepts. Well, in this case, what is going to make that numerator equal to 0 is negative 1. So negative 1, 0 is our x-intercept. Y-intercepts. We're going to plug in a 0 for all of those things. So, or all of the x's, sorry. So we're going to have 0 plus 1 over 0 plus 6 times 0 minus 2. It's going to be 1 over 6 times negative 2, which is 1 over negative 12. So our y-intercept is going to be 0, negative 1, 12. Alright, well, holes, we don't have any holes, so we don't have to worry about that in this case. But, again, we don't have very much information about our graph, so we're going to have to do some test points. So I'm going to choose something on both sides of those vertical asymptotes and another additional point in the middle to help me figure out what's going on. So if I choose, let's say, 3, I would end up with 4 over 9 times 1, which would be 4 ninths. So 3 and 4 ninths is 1 point on the graph. 4 ninths is just a little bit over, or a half. So it's going to be down there. Now I'm going to go to the other side. I'm going to say, okay, negative 7. That would give me negative 6 over negative 1 times, remember we're doing negative 7, negative 9, which would be negative 6 over 9, which would be negative 6 ninths. So again, that's going to be below. So I can see where those 2 branches are. Now I need to choose another test point to tell me what's happening in the middle, and I need to choose something in this range over here where I don't know where the graph is. So I'm going to choose negative 4. It's going to give me negative 3 over 2 times negative 6, which is negative 3 over negative 12, which is 1/4. So that tells me that negative 4, 1/4 is a point on the graph, which tells me that I'm going to have another one of those little snaky things. Sometimes they don't do that. Sometimes you end up with a U-shaped thing in the middle. But in this case, it was the snaky thing again. I keep on saying snaky thing. I'm going to get all these comments about how unmathematical I am. It's really a cubic type looking thing. So we have our graph. With those 2 vertical asymptotes, really the most important thing you have to worry about is more test points. It doesn't change too much about it. We can still find our domain though, and we're going to base our domain on those vertical asymptotes. So we're going to go from negative infinity to negative 6. Start up again after negative 6 to the other vertical asymptote. And start up again after that. So there we have the rest of our rational graphs that we are going to be looking at with our projects. Let's do a recap. I'm getting really into these recaps. I have them on all my videos now. Step 1, factor everything. When you have it in factored form, it makes it so easy to find that other stuff. Because then you just need to think about what numbers make the denominator 0. Those are going to be your vertical asymptotes. Numbers that make your numerator 0 are your x-intercepts. Factors that occur in both are your wholes, and you cancel those out. And the EBA, the end behavior asymptote, is using the ratio of the leading coefficients if the degree is the same. The bottom is bigger, it traditionally works out to be y equals 0. That's it for rational graphing. Again, what you have to do is practice, 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 and you will have no problems with it.